Okay guys, let's take a look at today's lesson. We're looking at derivatives of inverse trig functions. You're thinking, wow, this is fantastic. I get more formulas to learn. Yay, right? We don't have enough yet. Let's talk about what we have learned so far. We know power rule, right? One of our very first rules, probably one of our fondest memories, right? The power rule, pretty straightforward. Then we have learned actual trig derivatives, right? The derivative of sine is cosine. We've learned the product rule, the quotient rule. We've learned the chain rule. We learned natural log and log derivatives and logarithmic differentiation. So we've got a lot under our belt, right? We still have more to go. And this is derivatives of inverse trig functions, of the arc functions, arc sine, arc cosine, etc. So I like to look at patterns when I memorize things. So I want to talk to you about some patterns that help me here. Hopefully that'll help you memorize them. So if you notice, arc sine and arc cosine, their derivatives are identical. It's just one is positive and one is negative. Okay, so that remember the little rule that we use, or it's not a rule, but that all of the trig derivatives that start with a C were negative. Remember that? Derivative of cosine is negative sine. That holds true with the inverse trig also. If arc cosine has a negative, arc cosecant is negative, and arc cotangent is negative. So that holds true for these as well. If you can just remember, the ones that start with a C have a negative derivative. So I paired these two together in my head when I am memorizing because they are identical. One just happens to be positive and one is negative. Likewise with the arctangent and arc cotangent, these two, they are identical. It's just one is positive and one's negative. And lastly, our arc cosecant and arc secant. Here, they are identical, but the cosecant one, the arc cosecant one is negative, whereas the arc secant one is positive. So we really just have three more derivatives to memorize. Let's talk about them. They're actually very important. If we can think forward, I'll just kind of do a little bit of foreshadowing. So when we get into integration and we integrate things, you may have the integral of this. You would have to remember that that's arctangent, or that's how critical these are. That is how, because integrals are working backwards from derivatives, right? They are backwards. So my derivative, I'm going forward. So arctangent, the derivative of arctangent is 1 over 1 plus x squared, which is like, how in the world can an inverse trig function turn up with this derivative looking like something like this? That's kind of weird, right? You can. You'll probably be pleased to know it is possible to calculate those by hand. Right? I mean, if you really don't want to memorize these, you could go through this process right here. I used to work it all out, and students really don't use it, so I'm just going to point it out to you. How you could, yes, you can create them. You can generate these derivatives by hand if you have forgotten them, but really it would be easier to memorize them. So what would you do? You would turn, y equals arc sine x. You would flip the x and the y so you could turn it back into a regular sign. You do a triangle for it. Then you get to do the derivative implicitly. See, doesn't that look great? And then you come over here and then you rewrite it, and voila, we have our derivative. So yes, you can do all of them by hand. So another thing that we need to keep in mind is these are like templates. When we're taking the derivative of arc sine, we're going to use this as a template for our derivative because we're not going to have something just as easy as taking the derivative of arc sine. It's going to have other stuff with it. So that's what we're going to look at on the next slide. Questions so far? Okay. Let's turn, and we have a few examples on the next slide, so let's look at those. So the first thing that I would like to do as we are trying to find the derivative of arc sine of 2x, first of all, we need to recognize that we don't have a formula for that. Exactly, right? We don't, which usually means chain rule. That's what it usually means when we don't have a formula that looks like it. Not always, but usually. We see there's a 2x in there. That's a problem. That's not the rule. So this is a chain rule. So how in the world are we going to do a chain rule with those weird looking derivatives? You know, those are weird looking derivatives. So what I would encourage you to do is write the template for Arcsine. So just this plain standard derivative looks like this. This is our template. And what we're going to do is we're going to take the argument of the inverse trig function, and that is going to be substituted into this template everywhere there's an x. Okay, that's how we do the derivative, you know, with these. So I'm going to take this, I'm going to sub it in here where there's an x, and then I have to chain it, right? The derivative of 2x, I'd have to multiply by that. So that's the way these work, like a template. So let's see, the derivative of that is going to be 1 over square root of 1 minus. I'm going to insert a 2x right where that x was, because that's our first step, is to take the argument and insert it where the x's are. Our second step is to actually chain it, and so we need to take the derivative of the argument. The derivative of 2x is 2. And then our job is simply just to clean it up. We just need to clean it up and make it look nice. So it's 2 over square root of 1 minus 4x squared. And that's our very first inverse trig derivative. We okay with that? Okay, let's look at our next one. This one is using arc secant. And so I'm going to write its template up here. That's 1 over absolute value of x squared minus 1. That's the template for arc secant. Now, before I start the problem, I really do want to call your attention to these two templates. Probably some of the most, most errors involve these two, in that flipping these around. Is it 1 minus x squared or is it x squared minus 1? That usually is a big problem. And I will tell you how I remember, may be helpful. The way I remember which one is which is this one has an extra x value out here, and I think about these as wanting to be next to each other. That's how I remember which one is 1 minus x squared and which one is x squared minus 1, because you know they're different, they're opposite. So that's how I remember it is this one wants to be next to that x that's already there. Here it's the 1 minus x squared. Okay, hopefully that will help avoid that error. So let's see, this is our argument right here, e to the 2x. I'm going to take that, I'm going to insert it everywhere there's an x. So that derivative is going to be 1 over absolute value e to the 2x square root of e to the 2x quantity squared minus 1. Then I have to do what? I have to multiply by, I have to chain it. Multiply by the derivative of e to the 2x. So this is where I start saying, what's the derivative of e to the box? Because there's just going to be something up there, right? It's a box. The derivative of e to the box is e to the box times the derivative of the box. I mean, it's a chain, right? So the derivative of e to the 2x is e to the 2x times the derivative of 2x, which is 2. Now let's talk about these absolute values just for a moment. I would encourage you to write them, to put them in when you first do your derivative, and then decide whether you need them or not. Okay, deciding whether you need them or not is part of simplification process. We really should default to them. And we think about e to the 2x. We know that e to the 2x or e to the x, any of those, e to the 3x, those are always positive. Right? They never dip below the x-axis. So I really don't have to have the absolute value bars here. I really don't need them. Can I leave them there? Sure. It just wouldn't be fully simplified, but you could leave them there if it really bothered you and you were unsure whether you could take them off or not. So let's just clean this up a bit. So in the numerator, I would have 2e to the 2x over e to the 2x absolute value e to the 4x minus 1. Okay, so I can simplify. Those e to the 2x's would cross out, and I would be left with 2 over square root of e to the 4x minus 1. And that would be my derivative. Okay, how are we with that one? Okay, all right, let's look at our next one. Here, So we look at this and we decide when we take derivatives what template are we going to use. We need the overall template. For these I was able to use just the arc function's derivative as the template. This one though, what template do I need to use for this one? The product rule. I have to use the product rule. That's my template because it's a product. So FG plus FG, first things first, second things second. I'm using the product rule. So I take the derivative of the first thing, which is x, and I get a 1 arctangent root x plus, copy paste the first thing. Now I'm going to take the derivative of arctangent root x. Let me write the template of arctangent right here. So these are the templates that we're using. Okay, so I need to take my argument and I substitute my argument everywhere there's an x. Right, so I'm going to put it here, 1 over 1 plus. I'm going to put that in place of the x. Am I done? No. One of the most common mistakes is to forget the chain. Right, don't forget the chain. So I have to chain it. I have to multiply by the derivative of x to the 1/2. Right, which would be 1/2 x to the negative 1/2. Okay, so there we are so far. So now we need to clean it up. So we have arctangent of square root of x plus, let's see, we have x over 1. So square root of x squared would be x. So, and I have this 2 square root of x, 1 plus x. Am I done? Can you see any other simplification I need to do? Yes, there's one more thing. The x and the root x, right? I need to bring them into 1x, right? And they need to be together because they have the same base, right? This is x to the first and this is x to the 1/2. Remember our exponent rules, 1 minus 1/2. Remember all that? So we need to simplify that. So I have arctangent root x plus root x over 2 times 1 plus x. Now, before I start this last problem, I do want to talk about the inverse trig functions, the arctangent and so forth. A shortened notation for writing its full, I prefer its full name. I think that is less confusing. But unfortunately, there are many times where they will not write out its full name. And instead, they write tangent -1. Okay? We really need to completely understand that this is not an exponent. It looks like an exponent, and I really do not like this notation. I don't favor it. I wish that it didn't actually exist. I think perhaps they started it with the calculators. I'm not sure, but I think it's very confusing to students. This does not mean 1 over tangent. This is a name. It's a name. Remember in Algebra 2 and Pre-Cal when you would find the inverse function and then you would write f -1? Remember that? Okay, that -1 didn't say that it was a reciprocal. That meant inverse. That's what this -1 means, is inverse, not reciprocal. So I think that's really confusing to students, that this is not an exponent. So please be aware, on the daily work I have done a bit of each, just to make sure we're clear on when it's an exponent and when it's not. Okay, so this is a name. This just means arctangent. They wrote this instead of writing arc. I just wish they would always write arc. I think that's less confusing. But they didn't ask, so here we go. So let's take a look at our next one. We look at this, we determine how are we going to do the derivative, what rule are we going to use. We're going to use the arctangent template. Right, that's what we're going to use. There's no like power, or excuse me, product rule or quotient rule going on here. So the arctangent template is 1 over 1 plus x squared. So we look at that and we take the argument, right? We plug it into the template everywhere there's an x. So the derivative of arctangent is 1 over 1 plus natural log theta squared. So I just plugged it into the template. Now I have to multiply by the derivative of the argument. The derivative of natural log of theta. It would be similar to the derivative of natural log of x. What's the derivative of natural log of x? It's 1 over x, right? So what would the derivative of natural log of theta be? 1 over theta. So we multiply this by 1 over theta. And then it's just a matter of cleanup. So this would be 1 over theta times 1 plus natural log squared. Okay, so another important distinction here. Am I allowed to bring this 2 in front of the natural log? No, why not? This is a really this is a point students really mess up on too. Why can't I? Where does the 2 have to be in order for me to use that log rule? Yeah, it's got to be on the argument. It's got to be after it. It's got to be on this. It's not the function that's squared that allows us to pull the 2 in front. It would be if it were theta squared. If the argument were squared, then we could pull the 2 in the front, okay? We can't here. There's really nothing else we can do. That's it. We're done. Okay, so how is that? Yes?
If the 2 were after the argument,
So let's that's a good question. So what if it looked like this? Okay, then what we would do is we could bring it down here. The 1 really isn't a player in the whole situation. It's just this little term right here. The 2 would go in front of it. Okay? Any other questions? All right.